the functions. So let's define a few things so we know exactly what we're talking about. We have relations, and that's simply a rule that just maps between two sets of values. When you think about it, every one of our number plane graphs is a relation. There is some relationship between the x and the y value. So it might be something like this weird diagram. We've got the set of x numbers there on the left, the set of y numbers on the right, and there's all some supposed connection between these arrows, and the rule that does work here is simply x squared plus y squared equals 5. They all actually lie on the circle x squared plus y squared is equal to 5. So there's the relationship between the x and the y there. Now a function is a special type of relation. Okay? Uniquely maps from one set of values to another set of values. So uniquely maps. That means there's only one answer. So this time when we get the x values, now yes, you'll notice, where are we? -1 and +1 are both going to 1. That's fine. You can have two numbers giving the same answer, but each number in the x's only goes to one number. For any x value, there's a maximum of one y value. Could be that there's no y value. That's fine. That works all right. So that particular one would be y equals x squared would be the relationship that we're looking at there. An independent variable. That's the input of the function. So in most cases, the x values. Now, I don't know how you've been taught to draw your graphs in science, but I'm assuming they told you that whenever you're doing your experiments, you put your independent variable on the horizontal axis. And so that explains why the x-axis is the horizontal axis, because the x value in most functions are the independent variable. It's a free choice. We can pick any number we like. Now, domain, or sometimes called the natural domain, but most of the times we just say domain. So it's every possible value that when we substitute it in, we get an answer. If I look at the hyperbola, for instance, on the wall over there, I could substitute any value I like to get an answer except 1. Well, when I say 1, I don't mean the number 1, except for one value, and that value is 0. I can't substitute 0 into that one because 1 over 0, well, that's undefined. So 0 would not be in the domain of that particular function. And then sometimes we have a restricted domain. We might only be interested between certain values. A classic example, I guess, is, again, if we're dealing with some experiment or something, and time very often is the independent variable, well, then we're not really interested in negative numbers. You know, it's not like we conduct an experiment and go, right, let's start the experiment now. What happened 5 minutes ago? You don't do it, it's meaningless. So you would restrict the domain for that sort of thing to be t is greater than or equal to 0. Okay, the dependent variable then is the output, because it depends upon the value that we inputted. And the dependent variable we put on the vertical axis. So the range then is every possible answer. So if we use every possible value in the domain, put it into the function, all the possible answers is the range. So function notation, we often just write it like this. F is by far the most common one, I guess, F for function. It doesn't have to be an F, it could be any letter really. So we're saying y is a function of x. So that's indicating that x is the independent variable. F is representing whatever function we're using, and y is representing the dependent variable. So a very simple question. Say our function is 3x squared plus 4. Well, in function 5, if 5 is the input, it really is just a substitution question. Sub it in, 79 would be the output. Of course, there's nothing to say we have to substitute in a number. We could substitute in another pronumeral. So if I substitute in a, well, it becomes 3a squared plus 4. Everywhere I see an x, I replace it with an a. And this will become a classic one we'll see later on when we're dealing with calculus. Function x plus h minus function x. So everywhere I see an x, I'm going to replace with x plus h, and then I'm going to subtract the actual function itself. So 3 lots of x plus h squared plus 4 minus that original function, 3x squared plus 4. Tidying it up, we've got some, there's a bit of cancelling that'll happen there. And we get 6xh plus 3h squared. By just looking at a picture, how do we tell if it's a function? And the easiest way is just what we call the vertical line test. Because remember we said you could only get one possible y value. Right? So if I was to draw a vertical line, so something parallel to the y-axis, no matter where I draw it, it should only cut the curve once, if at all. As soon as it cuts it twice, I know not a function, because it's giving me two possible values. So here's our hyperbola, y equals 1 on x. Doesn't matter where I put the line, it's only cutting it once. If I put it at 0, it wouldn't cut it at all. That's okay. We just said it had to be a maximum of 1. So if it doesn't cut it at all, that's fine. So tick. Now let's have a look at a sideways parabola. That would have a function x equals y squared. And over on the left of it, it's fine, I'd miss it. But as soon as I go past the y-axis, it cuts it twice. So no good. So no, that's not a function, it's just a relation. Just a relation. It actually is made up of two functions. So the top half of the parabola would be y equals the positive square root of x, that's a function. And the bottom half is y equals the negative square root of x, that's also a function. But when we combine the two together to get x equals y squared, that's no longer a function because I can get two possible values for y. Alright, so domain and range for y equals function x. How do we find the domain? If you know what the curve looks like, that's the easiest way, because you can just look at the picture and go, oh okay, this is where the curve works. So geometrically I can just read it from the graph. Here's x equals y squared. I can just look at that, I can say, oh, the domain, well, the curve only exists on the right-hand side of the y-axis. Well, it also exists as 0. So I could say the domain is x is greater than or equal to 0. Here's one of these split functions, which is sometimes called step functions. So this one, domain is x is less than or equal to 0, but it also exists when x is greater than 2. Notice 2 is not included on that one. If you don't know what the picture looks like, what are the sorts of things we look for? Well, we know about fractions. What we know is the bottom of the fraction can't equal 0. So that might cause problems with the domain. We already talked about y equals 1 on x, so let's imagine, oh, we don't know what that looks like. So I'd be saying, well, hang on, I know the bottom of the fraction can't equal 0. So I know x can't equal 0, so the way I'd write my domain is, well, I could use every real value, except I can't use x equals 0. So all real x except x equals 0. Some people write all real x except x can't equal 0. I suppose it's all in the grammar, really. It's the same thing, because you could say, oh, it's all real x, except x is equal to 0. Can't have that. Or you might say, oh, look, it's all real x, hang on, except x can't equal to 0. Really means the same thing, but I tend to write it this way. X squared minus 1 on the bottom. Well, that means x squared minus 1 can't equal 0, so x couldn't be plus or minus 1. So we'd have all real x except x is plus or minus 1. Might have two fractions. Well, the rule's the same for both fractions, so x minus 1 can't equal 0, so x can't equal 1, but also 7 minus x can't equal 0. So x can't equal 7. So all real x except can't have x is 1 or 7. Square root signs, that can also cause problems because we know we can't find the square root of a negative number. So whatever's under the square root sign has to be greater than or equal to 0. Now you may or may not recognise this one. Anyone recognise? So what was that? Semicircle. Yeah, it's the top half of a circle or the semicircle. But we didn't know it. We'd say, well, look, 4 minus x squared is greater than or equal to 0. So x squared is less than or equal to 4. X must be in between minus 2 and 2. So there's our domain. We know x has to be between minus 2 and 2. Again, if you've got two square roots, both must be true. So x plus 3 must be greater than or equal to 0. So I know x is greater than or equal to negative 3. That's for the first one to work. The second one, x is less than or equal to 5. Well, both have to be true. So therefore, I'm just looking for the numbers that are in between minus 3 and 5 for this one to work. This one combines a fraction and a square root symbol. Well, the fraction said the bottom of the fraction can't equal 0. Square root symbol says it has to be greater than or equal to 0. So combining the two together, it's just going to be greater than 0. In this case, it can't be equal to 0. So I'm looking for x plus 2 is greater than 0. So it would just be x is greater than negative 2, the domain for that one. The range, again, geometrically, just look at the picture. So there's x equals y squared again. And you'll notice as we're going from the bottom to the top, there's no break in that curve at all. It's completely continuous. So its range is every possible value. We have all real y. Our step function there, okay, as we're going vertically, we've got y values that are less than or equal to 1, and also y values that are greater than 3. And by the way, when domain or range is all the values, don't just write all reals. Okay. Let them know that you know the range is talking about the y value. So you say all real y. Or if it's domain, you'd say all real x. Right, algebraically, what do we do with range? Maximum, minimum values. So even powers, they're always going to be positive. Absolute values, they're always going to be positive. Those sorts of things are what we're looking for. So y equals x squared, let's pick a simple one straight away. Well, I know that x squared always has to be greater than or equal to 0. So therefore, logically, y is greater than or equal to 0. There's our range. So if I had x squared plus 3, that would have to be greater than or equal to 0 plus 3, because the x squared has to be greater than or equal to 0. Range is y is greater than or equal to 3. 5 minus x squared. Well, now it's going to be a maximum, isn't it, rather than a minimum, because we're always taking away from 5. So it'd always be less than or equal to 5 minus 0. Absolute value, again, absolute value has to be greater than or equal to 0. So that one's just y is greater than or equal to 0. And if I had absolute value but then decide to subtract 5 from it, that one would always have to be greater than or equal to 0 minus 5, greater than minus 5. I mean, range can be tricky, because sometimes there's other things to look out for. But if there's a restriction on the domain, so like that semicircle, remember the domain was in between minus 2 and 2. You'd be surprised how often symmetry happens with these things. So I always check the endpoints, see what the y values are, and then I have a check in the middle, see what's happening there. And it gives me a pretty good idea of what's going to happen with the range. So there's that semicircle we had before. If I sub in 2, I get 0. If I sub in negative 2, I get 0 as well, don't I? But if I sub in the middle, I get 2. This is a nice symmetric one. So the range ends up being in between 0 and 2. I mean, if you can draw the picture, then it's just a heck of a lot easier. Fractions. If you have a constant on the top of a fraction, then it's impossible for that fraction to equal 0. I mean, you can't divide a constant number by something and get 0. Impossible. So y equals 1 on x. Let's go back to that one. Well, hang on. I know that fraction can't equal 0. So therefore, I can get every value, but I can't get y equals 0. 5 plus 1 on x. So again, that fraction can't equal 0. So I could never get the answer 5 for that one. So all the y's except y is equal to 5. Ooh, x plus 7, x plus 4. I find it easier to do a division first. You remember polynomial division? I mean, we'll look at it again later this year, but it ends up being that 1 plus 3 on x plus 4. As I say, you could do a polynomial division if you really wanted to, and go, x into x, that's 1, that gives me x plus 4. Do a subtraction, I get 3. But when it's in that form, now I can see, oh look, I've got a fraction there with the constant on top. That can't equal 0. So I know y can't equal 1 plus 0. So y can't equal 1. There are other ways of finding that, which we'll see later on. We could use limits as one way as well, once we do a little bit more work with polynomials. So, okay. Here's our first bit of work for today.